Assalamualaikum and hi everyone. Today, me and my fellow friends will present about chapter 1 electric charge and field. So, before we proceed, let me introduce you to my team members. The first one is Nur Masahar binti Hassan, which is me. Next is Kizaimah binti Amr Zaki, Anis Shakirah binti Azhari, and the last one is Nur Arisa Husna binti Muhammad Yusri. So the first subtopic is static electricity. The definition of static electricity is the result of imbalance between negative and positive charge in object. For example, when you're rubbing your hair to the balloon, the positive charge on hair and the negative charge on balloon will attract to each other that cause the hair to static. Next is electric charge. The definition of electric charge is basic property of matter carried by some elementary particles that control how particles are affected by electric or magnetic field. If you're rubbing a materials, it will not create any electric charge, but it will just transfer electrons from one material to another. Next is conservation of charge. The law of conservation of charge says that the net charge of an isolated system will always remain constant. In this figure, it shows that the nuclear process of beta decay, where a neutron decay to a proton and electron, the net charge before and after the event is the same. Next is insulator. So insulator is an substance or material that block or obstruct the flow of electric or thermal current. For example, is a plastic, rubber, and glass. Next is conductors. Conductors is a material that allow electron to flow through them easily. The electric charge is moved freely in response to an electric force. For example, water salt, uh, paper clip, and copper wire. Next is induced charge. The first induced charge is charging by conduction. It involves direct contact of a charged object to a neutral object. For example, when the rod with positive charge touch the neutral magnetosphere, the electron in the magnetosphere will flow to the positive rod because it attracts to the positive charge. Then it will left the magnetosphere with a positively charged. Next is charging by induction. So by induction involve of charging of one object by another without direct contact. The example is when we put the negative rod close to the neutral magnetosphere, the charge in the magnetosphere will align by itself to the opposite charge of the rod, and then the negative charge of the magnetosphere will flow out through the grounded wire, and it left the magnetosphere with positively charged. The last one is charging by friction. Charging by friction involves rubbing two objects together, where with one object will lose electron and the other objects will gain electron.
Hi, Assalamualaikum. My name is Kuzaima binti Amir Zaki, and today I will be explaining about Coulomb's law. Now, the definition of Coulomb's law is the electric force between two charges is proportional to the product of charges. So this means the product of the charges is Q1 and Q2, and inversely proportional to the square of distance between them. So the distance between them, which means the distance between the two charges Q1 and Q2 is represented by R squared, which is equal to the distance of separation. So in simple terms, Coulomb's law means it gives the electric force between 2 point charges. And this is the Coulomb's law formula that we will use in all calculations that needs uh, that we need to calculate the charges between Q1 and Q2 to produce electric force. So, matter can be electrically charged whether it is positive, negative, or neutral. Neutral, which means the charge is equal to zero. The force along the line connecting the charges is attractive if the charges are opposite. For example, in B, when Q1 is negatively charged and Q2 is positively charged, it will create a attractive force between the two charges Q1 and Q2, and repulsive if they are the same. So when Q1 and Q2 are both negatively charged, it will repulse. It will form a repulsive force between the both of the charges. However, neutral charges do not react with electrically charged object. So when, for example, if Q2 is neutral, which means equal to zero, therefore, it means there is no electrical forces acting upon the two charges. And the closer the two charges are, it shows that the stronger the forces between the both charges is formed. So the question that I have given to you today is, three charged particles are arranged in a line as shown in the figure below, where the charge A is equal to negative microcoulomb, charge B is equal to positive 10 microcoulomb, and C is equal to negative 12 microcoulomb. So this question, we need to calculate the net electrostatic force on particle B due to both of the charges A and C. So the first step um, to solve this question is by changing the unit of microcoulomb to coulomb only. So we need to um, use the prefix of negative 6 to replace the micro unit. So we need to do that on charge A, charge B, and charge C, and use the value K coulomb constant, which is this value below. Now, the next solution to solve this question is we need to find the force that is acted when A acts to the charge B. So, we use the formula F equals to K, QA multiplied by QB equals divided by the distance between them. So, the distance, which is 6 cm, needs to be converted into meter, and we will substitute the values of A and B into the formula given, and we will get the force of AB is equal to 125 Newton. And for the force uh, for A until C, we use the same formula where F is equal to K, and the charge of B and C is used in this formula, and the distance between A and C is used. So we substitute all the values into the formula, and we will get the force of AB, where it is 675 Newton. So the net electrostatic force of particle B is where we subtract the values 675 minus 125, we will get 550 Newton. So that 550 Newton is the net electrostatic force on particle B, which is acted by charge A and charge C. And with that, that is all for me for column saw. Thank you.
An electric field is a physical field that surrounds electrically charged particles and exerts force on all other charged particles in the field, either attracting or repelling them. The electric field is defined mathematically as a vector field that associated to each point in space the electrostatic or Coulomb force per unit of the exerted on a infinitesimal positive of the point. Then the SI unit for the electric fields, which is a volts per meter, exactly equivalent to the Newton per coulomb. The electric field can be visualized with a set of lines whose direction at each point is the same as the fields. As a concept introduced by Michael Faraday, he hypothesized that every charged object generates an electric field that permeates space and exerts a force on all charged particles in it encountered. And he was right. Electric field is a per- um, more measurable effect generated by any charged object. Okay, let's consider a positive point charge which we'll call capital Q to study the effect that the capital Q has on other charges. We'll bring in a small positive test charge, small q, and measure the force that acting on it. Now we will express it as an equation. The electric field creates a charge object is the electric force between the object and the test charge divided by the magnitude of the test charge, which is E equal to F over Q.
To find F, you just have to use Coulomb law, and you need to know the value of big Q, which is the point charge. F equal to K Q over R square. In fact, you can plug the equation for Coulomb law into this equation in place of F, which is 4, and if you do, you will see the magnitude of the test charge cancels out, and we are left an expression that relies solely on big Q. E equal to K Q over R power of 2. Now we are got equation to calculate the electric field generated by any point charges.
So let's see the field easy to picture and understand what is going on between these charges with vector using what we learned about Coulomb law and force vectors. A field line is a graphical visual aid and for visualizing vector field. It consists of an imaginary directed line which is tangent to the field vector at the edge point along its length. As a diagram showing a representative set of nearby field lines is a common way to depicting a vector with scientific and mathematical literature. So this is a called field line diagram. They are used to show electric field, magnetic field, and gravitational fields among many other types. In a fluid mechanism, field line is showing the electric field of a fluid flow are called string line.
So this is 4 important properties of electric field line. Firstly, the field line must be tangent to direction of the field at any point. Okay, this means if we place a positive test charge anywhere, the field lines will point in the direction of the force exerted on a positive test charge, just like a picture here. Okay, the next is the greater the line density, the greater the magnitude of the field. Okay, as a test charge move closer to one of the field charge, the force on it will be larger. This the greater number of lines in the area just shown in this picture, which is as apostrophe has the greater line density and the magnitude of the field line more than x. Okay. Okay, the next is the lines always start from positively charged object and end on negatively charged object. Okay, if there are no negatively charged object around, then the line just keep going on forever into infinity, seeking out negatively charged object wherever they can find them.
Okay, lastly, the line must never cross. Crossing line means the field is in different direction for charges in the same location, which is impossible. Okay, so that's all from me. Thank you.
Next, we move to the next subtopic is electric flux. The definition of electric flux is the electric field line that penetrate a given surface. Electric field lines are considered to originate on positive electric charge and to terminal negative charge. Electric flux is quantitative vector and flux equal to 0 when surface is parallel to the field. And the flux will be maximum when surface perpendicular to field. Okay, next is the SI unit is Nm squared over C. For a given uniform electric field E passing through an area A, the electric flux is defined as flux equal to EA cos theta. E electric fields, A is surface area. So next we move to the equation. Calculate the electric flux through the rectangle of sides 5 cm and 10 cm kept in the regions of uniform electric fields 100 and C -1 and the angle is 60 degree. Suppose theta becomes 0, so what is the electric flux? So the solution is we used the formula flux equal to EA cos theta. So we convert E to 100 and then we multiply with 5 and multiply with 10. Multiply with cos, we put the degree is 60 and then we will get 0.25 Nm squared C -1. So next we move to the next subtopic is Gauss's law. The definition of Gauss's law is the electric flux across any closed surface is proportional to the net electric charge enclosed by the surface. So yeah, the formula is Gauss's law equal to Qx closed over the surface, total surface. And then we need to know that Gauss's law is always true, but it's only for certain very simple problem with great symmetry. That's all from us. Thank you.